Hello. So now we are going to talk about chapter 7.1, kind of have another discussion of it. I already have a video that discusses 7.1, and this is just to give you, in essence, another run through it of the concepts, and also provide you a little preview of 4.2 and 4.3. So this is just, in essence, some more examples dealing with the concepts of 7.1. 7.1 is basically introducing you to the concept of what a sampling distribution is, and mainly, the terminology that goes along with it. So that's what the purpose of this video is, just to give you some other examples of that. And so our first video on chapter 7, section 1, it talked about these concepts, which we've talked about these really throughout the year, is that what is a population, a parameter, a sample, and a statistic, and exactly what is a sampling distribution. So it's important to note that a population in the world of stats is just a whole group that you want to know something about, the whole group of people, animals, or things that you want to know something about. The parameter is what you want to know. It is, in essence, a number or a value that describes the whole population. And it could be a mean, which is a mu. It could be a p, which is a proportion. It could be a sigma, which is a standard deviation. Or it could be like a population median, which we don't have a little notation for, or a population interquartile range, or a population 30th percentile, et cetera. But the main ones that we're concerned with are mu and p, the mean and the proportion, as far as parameters that we're trying to estimate. In order to find those numbers, we need to take a census. In other words, we would need to measure everybody in the population, or everything in the population. So, but many times we decide to sample. In other words, take a subset of the population and study that. And that's what a sample is. It's critical that we get this sample how? That's right, randomly, that we get it randomly, that everybody or everything in the population is equally likely to be chosen, and that prevents bias. All right, then what we do with the sample is we calculate a statistic, which is just a value that describes a sample. So we could find the mean of a statistic, let's say the mean test score from our sample, or the mean height from our sample, or the mean weight from our sample, and so forth. If it's a mean, it's an X bar, and that estimates mu. Okay, or we could be finding a proportion, the proportion of the apples in our samples that are rotten, or the proportion of students that have passed the test, or something like that. But if it's a proportion, it's a p hat. The hat means it's an estimate, and it estimates p. And the sample standard deviation, S, is an estimate for sigma. So that's what a statistic is, just a value that describes a sample. All right, then what is a sampling distribution? Well, whenever we do sampling like this, and so we have a population, so let's say, for instance, for the students at Grissom, let's say there's 2,000 students, and let's say the mean weight of all the 2,000 students is, I don't know, but let's just pretend it's like, let's pretend it's like 159 pounds, okay? 159 pounds, all right? And we would have to weigh all 2,000 students to find that, but we can't do that. So what we decide to do is we take a sample of, let's say, size 30, and we find that their mean weight is like 157. So what's happening here? So here's the true population value. The parameter is 159, and then the X bar, in this case, is down here. But we say to ourselves, well, if we were to take it, anytime you get a sample value, you say, well, if I had taken another sample of size 30, so in sub 1, let's say another sample of size 30, and I weigh them and find another sample mean, sample X bar, I'm going to get something different, maybe 161.2 pounds. So that's up here. And if we took another sample and found another X bar, and if we took many samples and find many X bars, this collection, this family of X bars, is referred to as a sampling distribution. It is every value a sample statistic could take. So whenever you take a sample and get a statistic, you should say to yourself, it's just one of many I could have gotten. And in so this case, this is what the sampling distribution in essence would look like if we kept going on. So you'll notice in this case, it's starting to look approximately normal. We'll talk about that later in the chapter. But that's what a sampling distribution is. And we have a very similar thing going on with the proportions. So with a proportion, let's say you want to know the proportion of students, let's say, that went to Challenger Middle School. And so that would be a proportion. And so that would be P. And let's just pretend it's like 30%. Let's say pretend it's, but we don't know that. So we take a sample of, let's say, 100 students, and we find that, let's say, 28 of them which is Challenger from that. But that is our estimate. And we realize we put a hat on that because it's an estimate. And so we would say to ourselves, well, whenever we take a sample, we think, what does my sampling distribution look like? Well, our p hats are mostly going to be around p since it's the true value, but because of sampling variability, they are going to vary in repeated sampling of many samples of the same size. So p hat, so there's a sampling distribution with proportions, p hats. And so what is a sampling distribution proportions? It's every value p hat could possibly take in repeated sampling. And we're going to use this concept to do calculations later in the chapter and really throughout the year. So those are the two main kinds of sampling distribution we're dealing with. So what is a sampling distribution? It's every value a sample statistic, whether that be X bar or p hat or S or any other sample statistic, could take in repeated samples of the same size from the same population. And we say that an estimate is an unbiased estimator if the mean of our sampling distribution is in fact equal to the true value, equal to the true value of mu or the true value of p. So that's an unbiased estimator. So those are the basic concepts. So Leslie, and we did examples in that regard in the other video, but let's do some more examples, and then I want to do a little preview of chapter 7, section 2, and chapter 7, section 3. So in this particular example, all right, so this is the sort of thing that could happen on the exam. They're not going to ask you to define terms like this on the exam. What they're going to do is they're going to give you a context and ask you to pick things out of the context like this. And this is what your quiz is going to look like on 7.1 and 7.2. So the quiz will mainly be something that looks like this. It'll be a context and ask you to identify the population, sample, parameters, statistics, and so forth. So you got to be able to do this. And then there will actually be a problem similar to this on it, which we're going to talk really more about that more thoroughly in chat. This should be chat. Why does that say 4? That should say 7.2. That was silly of me. And this should say 7.3. We're in chapter 7 now. So anyway, okay. So anyway, so let's see if we can do this problem. So this one says a teacher wishes to estimate the mean. Okay, not the proportion. So that's sort of the first thing is you identify. So the mean, now I'm dealing with X bars and mu's, not p hats and p's. Okay, so the mean amount of time that students at our school spend studying or spend doing homework each week. There are a total of 2,319 students at our school. Unbeknownst to the teacher, the 2,319 students spend an average of 4.9 hours a week doing homework with a standard deviation of 1.6. She takes a simple random sample of 40 of the students, so that's good. That means we don't have any bias in our sampling method, all right, and finds that they have spend an average of 5.2 hours a week doing homework with a standard deviation of 0.9. Identify the following. Okay, what is the population here? What is the whole group we want to know something about? And it is all the students at the school. That's the group we want to know something about. So the population is all the 2,319 students at this school. Population is the entire group you want to know something about. So don't just say all the students. You know, don't just make sure and state that because maybe you could be referring to the sample there. So make sure you're clear about that it's all the students at the school. What is the sample? The sample is the subset you're actually studying, and that is the 40 in the sample. So the 40 selected students, that is the sample. Okay. What are the parameters? Parameters are numbers or values that describe the population. So it's either, most of the time, it's going to be a mu or a p. And so in this case, we have a mu. It said, unbeknownst to the teacher, those students spend an average or a mean of 4.9. So the parameters are that mu is equal to 4.9 hours, and put the units, by the way. And we have another parameter with a standard deviation of 1.6. So that's a sigma because it's a population standard deviation. We use a Greek letter sigma. And so that would be 1.6 hours. So those are our two parameters here, our two numbers that describe the population. What are our statistics? Statistics are numbers that describe the sample. So what numbers do they get from the 40? Well, we have an X bar, an average or a mean of 5.2 hours. And then the sample standard deviation, we denote with an S. I wish they put the hat on the S, but they don't. So a 0.9 of an hour. So there we go. There's our statistics. All right, so how would you describe what is the population distribution? A distribution is a list of numbers, effectively is what it is. And so it's a list of numbers that are in the population. And so in this case, we got 2,319 students, each of which is going to have a different amount of time they spend studying. And so you would say the study times of all the 2,319 students. So the population distribution would be a list of 2,319 numbers. Okay, it's every number that's in the population. What is the sample distribution? A distribution, once again, is a list of numbers. That's what it is. And so it's all the numbers that are in the sample. So you've got 40 people in the sample, each of which has a different study time, basically. And so you would say the study times of the 40 selected students. So that's that. And then what is the sampling distribution? That's very different from the sample distribution. The sample distribution is those list of 40 numbers. The sampling distribution for a mean is every value X bar could take in repeated sampling. Now, in this case, we only took one sample, but a 5.2. But a sampling distribution is sort of a theoretical thing of you realize this is just one estimate of many that I could have gotten. And all the ones I could have gotten, that's what a sampling distribution is. And so it is every value X bar could take in repeated samples of size 40 from this school, from the same population from this school. That is what a sampling distribution is right there, okay? Don't get the two terms sampling distribution and sample distribution mixed up. And that's sort of the terminology, and that's section 1 effectively. Now, we've also got proportions that's a very similar sort of thing, so we need to talk about that. But first of all, I want to do a preview of what happens in chapter 7, section 3, and the sort of problem you can look forward to there. All right, so this one says this. It says the teacher above takes another sample of size 40 from this population and finds the mean amount of time they spend doing homework, okay? So it finds another X bar. Assuming that the true population mean is 4.9 and the standard deviation is 1.6, which that's what they were, according to up there, what is the probability that her sample mean would be greater than 5 hours? Okay, the probability would be greater than 5 hours. And so what we're going to do, and then does this result give you reason to doubt that the population is in fact 4.9 hours? Why or why not? So we are going to use the concept of a sampling distribution to answer this problem. So our sampling distribution, okay, is going to be sent, the true value is 4.9. Our sampling distribution is every value X bar could take in repeated sampling. So it's all these values of X bar, okay? And our sampling distribution is going to look like the normal curve, and we'll talk about this more thoroughly in section 4.3, but it will be approximately normal for a mean because our sample size is greater than or equal to 30. And that's what we're going to call the central limit theorem, is we have it, these X bars are going to vary approximately normally whenever your sample size is bigger than 30. It's a different thing for proportions. That's what it is for means, okay? The mean, and so we have some formulas here we're going to use. So the mean, the middle of these X bars, the mean of these X bars will in fact equal mu, which is 4.9. The X bars will be centered around the true value. But here's where it's a little bit different. The standard deviation, what's the standard deviation? In other words, how far do you got to go out to go to halfway down this hill? And of course, that's the other value we're going to have to enter in normal CDF. The standard deviation of these X bars is, and here's our formula, sigma over the square root of n, okay? And that is what, if you turn to the second page on your formula sheet and you go down where it says means, the mean of the X bars, the parameters for a sampling distribution, the mean of the X bars is equal to mu, the standard deviation of the X bars is equal to sigma over the square root of n. So we take the sigma, our sigma is 1.6 in this case, and you divide it by the square root of the sample size. So that's the little trick of section 3. So let's see what that is. And so our standard deviation is going to be 1.6 divided by the square root of 40. And so that, in fact, is approximately equal to 0.25298. Okay, now we can answer the question. What is the probability that our X bar, our sample may be greater than 5? Okay, now 5. So if we go up 1 standard deviation, if I go 4.9 plus that, that's going to be 5.1298 to right there. So 5 is like right here. So 5 is like right there. So what's the probability that it'll be greater than 5? So that would be on up here. Okay, and so we will say normal CDF, just like we did in chapter 2 and like we did in later in the year, greater than 5. So that'd be 5 to infinity. Our mean is 4.9, and our standard deviation, you can just go ahead and write 1.6 divided by the square root of 40. Just write it like that. Of course, label this as lower bound, upper bound, mean of the X bars, sigma of the X bars, like that. And let's see what we get. And so we go second, remember normal CDF, if you go distribution, second VARS, which is distribution, normal CDF, we're going 5 to infinity. So you can just 5 to hit 9 billion or whatever. Our mean is 4.9 and our standard deviation is 1.6 divided by the square root of 40, right like that. There we go, boom, boom. And we get 0.3463 about. 0.3463, like that. And that is the main problem from chapter 7, section 3. We're going to be going through that a little slower when we do chapter 7, section 3. And so does this result give you reason to doubt that the true population is 4.9? In other words, is our sample value here, is it so weird where we're saying, do we have reason to doubt the 4.9 is true? And in this case, no, it does not. 5 is reasonably close to that. And what this number is a p-value. It's the probability of getting a sample value this unusual or more unusual just by chance. And this is above 0.05. And so what we're going to say is, does this result give us reason to doubt? And we are going to say, no, it does not, because 0.3403 is greater than 0.05. That's sort of our, what we're going to call our alpha value. And we'll say, so it's greater, thus it, meaning 5.0 in our sample, thus 5.0 hours would reasonably occur by sampling variability, or in other words, just a natural difference just due to chance, by sampling variability. If it was below 0.05, if the probability of this happening was below 0.05, we would say we have reason to doubt it because it really wouldn't reasonably occur by sampling variability, or we'd say it's not really a plausible occurrence, we could say. There's different ways you can word that, but there you go. And so now let's look, and so that's, the terminology from section 1, and that's really the main sort of problem in section 3. And so let's look at this. So this is more section 1 stuff right here. This context 2 deals with proportions, and proportions are going to be used in chapter 7, section 2. So let's see what we got here. The teacher in context 1 wishes to know proportion. Aha. So now we're in this world, the world with proportions and p hats estimating p's, okay? And there's going to be a different little place in our formula sheet. The top of page 2 in our formula sheet, dealing with proportions, and our formula is a little more complicated. That's okay. All right, so it says the teacher in context 1 wishes to know the proportion of the 2,319 students at our school that had a detention in the past school year. Unbeknownst to her, 744 of the 2,319 students, which is 32.1%, had a detention this past school year. She takes a simple random sample of 200 students. Good. Simple random sample. We got a random sample, so we don't have bias here. So we have an unbiased estimator here, and finds that 61 of them, which would be 30.5%, had a detention the past school year. Identify the following. The population. Once again, the whole group you want to know something about. All the 2,319 students at this school. Okay, what is the sample? That's the subset you actually study. In this case, she takes an SRS of 200. You would say the 200 selected students, the 200 selected students. The parameter, what's the parameter? That's a number that describes the whole population. And so in this case, it is a proportion. It is P. It is the P, which is equal to, 32.1%. Now there's different ways you could express that. You could, you could put it as a decimal. Most of the time I use decimals, 0.321, or you could use a fraction, and the fraction would be 744 divided by 2319. So it's going to be in one of those three ways. Okay. Any of those three ways are acceptable, and that you have to be comfortable with any of those three ways of expressing that. All right. What is our statistic? Our number that describes a sample. And in this case, with a proportion, it's going to be a P hat. Statistics, we like to put hats on them. And so it's P hat is equal to the proportion in our sample, which is 30.5%, or you could write that as P hat is equal to, in decimal form, 0.305, or you could put that in fractional form, our P hat, which would be 61 out of 200. So, right? Yeah. So there we go. There's our statistic. All right. So what is our population distribution? Now, if you think about this, there's really the population distribution is the list of numbers in your population, but you really don't have numbers in your population. You're just labeling people as whether they've had a detention or not. Okay, so there's no numbers in the population. It's just detention or not detention. Everybody's labeled with that. Like in this case, everybody's got a different number. Okay, their number is how long they slept. And so so-and-so, or not how long they slept, I'm sorry. It's how much time they spent doing their homework. And so everybody has a different number. So there is a population distribution, but here there is not one. There is not one. There's not a list of numbers in the population, so to speak. Same thing with the sample. You don't have like 200 different numbers in your sample. You've got 200 statements that are either had a detention or not have detention. There is not one, but there is a sampling distribution. There is values for P hat. Each sample of size 200 in this case is going to have a proportion that have had a detention. This particular sample had, 0.305. If you took another sample of size 200, you may get like 0.356 or 0.355 or something. Okay. So every sample, and so could have a different number. And so what is the sampling distribution? It is every value that P hat could take in repeated samples of size, our sample size is 200 from this school, from this same population, from this school. That is what a sampling distribution is. Every value P hat could possibly take. Okay. So, and that is in essence, once again, the theory of section 1. Okay. Now let's do a preview of section 2. So what we're going to do with this concept is we're going to be able to make calculations. All right. So the teacher in context two takes another sample of 200 students from her school. She finds that 50 of the 200 have had a detention. What is the probability she would get a sample proportion this low, 25%, assuming that the true proportion is in fact 32.1%, which is what it said it was up there. And does this result give you reason to doubt that value of 32.1%? Why or why not? So what we're going to do is we're going to find the probability, assuming this 32.1% figure is true, what's the probability of getting a sample portion, a p-hat of 25% or less? So we've got to think about the sampling distribution, and I'll use decimals here. So it's saying our sampling distribution has a mean of 0.321. That is what is our parameters equal to. Our sampling distribution is every value p-hat could possibly take in repeated sampling. Most of them, because 0.321 is the true value, be around 0.321. Okay, these will vary approximately normally, and we'll talk about the rule for this more extensively in chapter 7, section 2. It's going to be approximately normal if n times p and n times 1 minus p are greater than or equal to 10. And we'll talk about, you have to memorize that for proportion. So our n here, our sample size is 200, our p is 0.321, and then you'd say 200 times, and then that would be 0.679. And let's see what those are. So we'll say 200 times 0.321. And so that's equal to 64.2. And then we will say 200 times 0.679, and that's 135.8. So that's 135.8. They are both greater than or equal to 10. Thus, we will say normality is met. Normality is met. We can use the normal curve. We can use normal CDF here. Okay, now the next question we have is we want to find how unusual would it be for one of these p-hats to be 0.25. But where is 0.25 down here? Is it way on the tail or is it up here? So the way we figure that out is by the standard deviation. And so that one standard deviation would be halfway down this hill there. So how far is it to there? Well, that's what these formulas tell us right here. So here's on the second page of your formula sheet for proportions for the sampling distribution. The mean of the p-hats is equal to p. Okay. The standard deviation of the p-hats is equal to this formula, the square root of p times 1 minus p over n. So our standard deviation of our p-hats is equal to the square root of p times 1 minus p over n. In that case, this is equal to the square root of 0.321, that's p, times 1 minus that, which would be 0.679, right, over 200. And let's see what we get. Let's see what we get. So we shall say the square root of 0.321 times 0.679 divided by 200. And so we get our standard is 0.03301. So if we go down one standard deviation from there, so if we say 0.321 minus that, so we get 0.29 about 0.288. So that's about 0.288. So that's one. So it's 0.25 is somewhere down here pretty far. And so let's find this p-value, this probability of getting a value this low or lower. And so we'll use normal CDF for that, right? So we'll say normal CDF. Normal CDF. Our lower bound is negative infinity, just like we did in chapter 2. Our upper bound is 0.25. Our mean is 0.321, and our standard deviation is about 0.03301. Label this as lower bound, upper bound, mu, and sigma, like that. And so let's see what we get. And so we'll go second VARS, which is distribution, normal CDF. So our lower bound is negative infinity. So I'll just go negative 9 billion or something, and then to 0.25. That's our upper bound. Our mean is 0.321. And then our standard deviation, we'll just enter 0.03301 about. And so that is equal to 0.01574. Okay. So our p, so in other words, it's only going to happen getting 0.25 or less is only going to happen about 1.5% of the time, just by chance, assuming that this 32.1 figure is true, is the true proportion. The probability we would get a sample value of 0.21 or less only happens about 1.5% of the time. Therefore, it's really unlikely to happen. And we got a good random sample here. Got a good, random sample. She took another random sample, right? Yeah, good random sample. So we know we don't have bias. So why is it this different? And so what we would say is this gives us reason to doubt the 3.21 figure. So it says, does this give you reason to doubt? And so we would say, yes. And why? We'll say this, because this is bigger than this is smaller than 0.05. Because 0.01574 is less than 0.05. It's less than 5%. Thus, a p-hat of 0.25 is unlikely to occur by sampling variability only, by sampling variability. And that's it. That is your section 1 and then a preview of section 2 and section 3. So I hope that was a good experience for me. Please send me questions. Please send questions. Please send questions. Okay. That would be great. I would like that. And so I hope you have a great day. Thanks for stopping by.